Hi, I'm Richard Overdorf with Agilent Technologies. Today I'm here to show you the wideband analysis solution. This is a new capability from Agilent that offers 1 gigahertz worth of bandwidth. It's an easy-to-use solution that features automatic correction data. This solution is very useful for people in electronic warfare, radar, or wideband communication systems. Today I'm going to show you how this solution works, but let's first get started looking at the configuration. So the setup consists of 3 things. The first is a PXA signal analyzer, the second is a high dynamic range oscilloscope, and finally the vector signal analysis software. The PXA's IF output is connected to the channel 1 of the oscilloscope. In addition, there is a LAN cable connected between the oscilloscope and the PXA signal analyzer. Also, we have a wideband arbitrary waveform generator and a vector PSG to generate these wideband signals. The M8190's differential IQ outputs are connected to the vector PSG's IQ modulator, which then upconverts a signal up to 44 gigahertz. Our analysis solution can demodulate or analyze signals up to 50 gigahertz. Next, let me show you how the VSA software controls the hardware. So here we see the VSA software, and we're going to go into the macro menu, and we're going to select the wideband tuner, and we're going to run the wideband tuner. And this software component is going to pop up a screen where you enter the IP address of the tuner, which in this case is the signal analyzer. So you type in the IP address, and then you hit the button that says Connect to PXA. And then after you do that, it's going to set up the VSA software and control the PXA. Then you set your center frequency, your RF span, and pick your IF frequency. In this case, we're going to do 800 megahertz, so we're going to change this IF frequency to 500 megahertz. When you hit the Set button, it configures the VSA software and controls the PXA signal analyzer. You can see that I have a CW signal at 10 gigahertz. Next, I'm going to go into the input menu, and I'm going to show you where the software component added in the correction files. There's an RF correction file, an IF correction file, and in the middle there is a frequency converter section that puts the IF center frequency as well as the IF bandwidth, and it inverts our spectrum, so everything is set up on the VSA software as it should be. And you can notice in the background it also has the right span and center frequency in the VSA screen. So we have a signal at 10 gigahertz. Now I'm going to start that signal to sweep across the screen. So after we sweep across the screen, what I want to do is show kind of an indication of how well the IF corrections perform versus not having any corrections. I'm going to select the peak hold value in the averages menu, and I'm going to do a continuous peak. So every sample on the screen is going to be at its maximum based on what is measured. Now I'm going to change the reference value and change how many dB we have per division, so we can easily see subtle differences from the amplitude across the band. So you can see that this is with the corrections off, and we have approximately slightly less than 10 dB worth of variation across the band. And when I turn the correction values back on, so this is the stuff that the software component added, now you can see that our variation is 2 dB. This includes the amplitude variance from the source, and it also is a family correction. This is not a box-specific correction. This correction could likely be better in your setting. So now we're going to go back to our software component, and I'm going to set up the PXA to have a center frequency of 18 gigahertz and a span of 400 megahertz and an IF frequency of 322.5. In this case, I'm going to have the user corrections on, and the converter already implemented all of the corrections that we need. And I'm going to input a QPSK signal, and I'm going to demodulate that. And I'm going to show you what that performance looks like. I'm going to pause the measurement, and the EVM is around 2.5%. Next, I'm going to demodulate a APSK signal. And so I'm going to recall this setup. I'm going to go into a wider span. First, I'm going to show you user corrections off, and then I'm going to show you with the user corrections on. With the user corrections off, you can see that we're unable to demodulate the signal. In the demodulated properties, we have the symbol rate. We do not have an equalization filter on. In the Advanced tab, we have defined the APSK ring ratios. Next, I want to show you the corrected version. You can see in this case, we have a EVM of about 3.3%. This signal is likely to have an inherent EVM of somewhere between 2 and 3%, meaning the residual EVM of the system is pretty low.
Today I showed you the wideband analysis solution. We showed wideband analysis of signals up to 1 GHz, carrier frequencies of 50 GHz, and we showed that it was easy to use and also easy to set up. For more information on this product, please see the URL on your screen, and thanks for watching.